Hello.
Hello.
Yeah, so by the way, I'm aware that I owe you, at the end of this lecture, I will need to upload three Zoom videos. One of them, I guess I should strip off some discussion first and then I'll upload it. So I apologize for that. I should be able to do that by the end of the day for sure. Yeah. Okay. Any other questions? So I want to remind people that I'm looking for volunteers to do things on the Friday, to present things on the Friday meetings. In particular, I really did essentially skip chapter 5, very short chapter on cohomological dimension of profinite groups. So I would encourage someone to take a look at that. And I really think you could get, I think maybe like half an hour or something, you could cover most of the results in chapter 5 without, I mean, you don't have to prove what you don't want to prove. But, okay. And I guess on Friday, Freddie can tell us more about the problem that he was working on. So he had contributed a write-up of this duality between homology and cohomology for finite modules over finite groups. Okay, yeah, anything else? If not, we proceed. So today we actually do Galois homology, like for real. So that's exciting. Let's see. Okay, yeah, no, this was a fairly hastily prepared lecture. I think maybe even the handwriting will show that, but see what happens. Okay, so Galois homology. Well, if we have a field, then we define the absolute Galois group to be the automorphism group of a separable algebraic closure of the field over the field itself. Yes, I think so. Harari notationally, as I mentioned at the very beginning of the course, his notational convention is to use K bar for the separable algebraic closure instead of the algebraic closure. I don't have any specific beef with that convention. In fact, I seem to recall that I used that myself in at least one paper, but I think that pedagogically, I mean, it's cleaner to say that, but it's a little bit awkward to write like K supersep supercross, for instance. That's going to come up a lot. But I think maybe it is helpful to remember that, the distinction between the separable closure and the actual algebraic closure, which of course is only a distinction when the field is not perfect, but it might not be. Local and global fields of positive characteristic are not perfect. So yes, I'm probably just going to write SEP. Okay, so that's the absolute Galois group. He has some different notation for that. So that is a profinite group. Yeah, so first there's an interesting functoriality here. So if I have a totally arbitrary field extension. So again, in practice for our course, we would probably be happy to have this be an algebraic field extension, but it does come up to have to do this for transcendental field extensions as well. So first of all, you can always extend any field extension to a map on separable closures and also on algebraic closures, but maybe you do it on algebraic closures first, and then you check that it takes the separable closure into the separable closure, and that's how you have this map. There's a choice. First of all, you have to choose a separable closure, and second of all, you have to choose a map. And so if you sort of think this through for a little while, I'm certainly not in a position to say that there's a unique such map. So that minor concession to that has to be made later. And so then the next claim is that if you have you take a field embedding, you extend it to an embedding on separable closures. So I claim, following Harari, that induces topological group homomorphism from the absolute Galois group of the bigger field to the absolute Galois group of the smaller field. Okay, so why is that? Well, so if I take an automorphism of L-sep, I would kind of just like to restrict it to K sep, but if you sort of think about it, if L over K is transcendental, maybe you should think a little bit about why, if you restrict an automorphism to K sep, then it still has values in K sep, right? And so the reason for that is that, well, this automorphism by definition fixes L pointwise, and K is contained in L, so it fixes K pointwise, right? And so therefore, if you fix K pointwise, then I think you'll find that any element that is algebraic over K, the automorphism, if you just look at its minimal polynomial, then the automorphism is going to preserve the minimal polynomial, and so therefore it'll take any element that is algebraic over K to one of its conjugates, and so therefore it will actually take the separable closure to the separable closure. Okay, so whatever, it needs a little bit of thought maybe to make sure that this restriction map is is actually well defined, but it is. Okay. All right. Yeah, and so again, the most important case of this presumably is when L is an algebraic extension of K. And then what are we doing? In that case, at least, we are going to get we're going to get the automorphism group of L, absolute Galois group of L as a closed subgroup of the absolute Galois group of K. Okay, I guess, yeah, I didn't think of it. In general, I don't know that I'm claiming that this map is, let me just think for a second. I don't think I should be claiming that this map is, yeah, no, if L is transcendental over K, there's this map should not be injective just because you fix K sep pointwise. Why does that mean that you should fix L sep pointwise? Well, if it's algebraic, then sure, because K sep is equal to L sep, and otherwise that doesn't sound very good. Yeah. So this map should be an injection when the field extension is algebraic and maybe not in general. Okay. So if I take a discrete GK module, that's our sort of object type suitable module for profinite cohomology, then we get this restriction map from the Galois cohomology of K into the GK into the Galois cohomology of GL. Okay, it's just coming from, it's just one of these functorialities coming from whenever you have a continuous homomorphism from one profinite group to another. Again, you just have this pullback map, this contravariant functoriality in the group. And so again, on the level of cochains, you're literally just taking your cochains, with domain domain GK to the something and pulling them back to cochains with domain GL to some power. Okay, so it should be pretty clear that you have this map. And again, I would call this, it would be reasonable to call this a restriction map. Okay. It turns out that this restriction map is independent of the choice of the extension to the separable closure. So that I will let you consult Harari for the explanation. It has to do with the fact, another fact that I skipped, which is that a conjugation map on the group side is going to induce the identity on cohomology, which I've said that before, but anyway, you have to prove that. Okay, so it's a fairly benign change of groups type of argument. Okay, and so therefore this is what we usually do. We write, if we know that the profinite group that we're interested in is the absolute Galois group of K, then why do we write, instead of writing GK all the time, we just write K. So Galois cohomology HQ KM means profinite group cohomology where the profinite group is the absolute Galois group of K, and M is a discrete is a GK module endowed with discrete topology for which that makes the action with an action of GK. So that's continuous for the curl topology on GK and the discrete topology on M. Okay. All right, and so as I mentioned last time, one really nice consequence or one case of this is if you take a commutative group scheme over K, then you plug in the K sep points and that becomes a discrete module. And so in particular, we can look at the Galois cohomology. I can we can abbreviate even more, and we can just do HQK of A means Galois cohomology with coefficients in the K-sub point. So this just turns out to be this just turns out to be very interesting depending upon what kind of commutative group scheme you have. The simple examples I'm going to do on the next page or something. I'm going to do the case where the commutative group scheme is just the additive group of K. Then we're going to talk about the case where the commutative group scheme is a multiplicative group of K, and then more or less every commutative linear algebraic group is going to be built up out of a number of copies of the additive group and the multiplicative group, more or less. And then the other interesting case is if your commutative group scheme is an abelian variety. And so I was talking about that in the course last spring. Unfortunately, I don't know if it's unfortunate. I don't think I'll be talking about Weierstrass groups of abelian varieties in this course. But if in particular, though, for any, as I defined before, the Weierstrass group is most often only called the Weierstrass group when it's an abelian variety. But for any commutative K group scheme, you could define the Weierstrass group of A over K to be first Galois cohomology with coefficients in the K-sub points of A, and that's a fascinating cohomology group. All right. So here I think, yeah. So this is a little bit. I think I just remembered that I wanted an exercise that I mentioned. I kind of blurted out last time. So for any field, this is not a great notation. Capital N sub K will be the supernatural order of the absolute Galois group of K. So I kind of said the definition quickly last time. If you look in chapter 4 of Harari. So again, what is this? If you basically you look at the orders of the finite quotients by open normal subgroups of G, and then you kind of you use the orders of those finite quotients to define a supernatural order. You do this prime by prime, and then if every finite quotient, if there's a maximum power of P that divides all finite quotients at the same time, then the supernatural order at P is that power of P, if the finite quotients of G become arbitrarily divisible by P, then the supernatural order at P is infinite. Okay. Anyway, so that's a supernatural number, so it's a formal product over prime powers, and then each exponent is either a non-negative integer or is infinite. And so then then the exercise here, which I think I said before, I mean, even for you can say it for profinite groups, you can say it for Galois groups, it really comes to the same. Then every Galois cohomology group with index dimension at least 1 is torsion from the supernatural order of the Galois group. Okay, so for instance, if your group was a pro-P group, then all of your Galois cohomology groups would be P prime rank torsion. Okay. I mean, I suppose in practice, unless you're restricting to CELO P subgroups or stuff, in practice, maybe I should say this. Then you could ask yourself, like, what is the supernatural order of various fields, right? And unless you build it to be small, the supernatural order is probably the product over all primes of P to the infinity. Okay, so maybe that's another exercise. I think maybe I've been stating some exercises and I haven't been coming back and sticking them in the file, so I should do that. So exercise, compute the supernatural order for K. I don't know, you guys can ask me, what fields do we care about? I guess we could do algebraically closed, that's silly. The group is trivial. We could do the real numbers, or real closed. If you know what real closed is, it's not gonna take you any more time. You could do a finite field. You could do a local field, and you could do a global field. But the point being, as you go down the list, in most cases, the supernatural order is just going to be the product of p to the infinity as p ranges over all primes p. Okay. I mean, another way of saying that is like, do you have finite degree separable extensions that are divisible by arbitrarily large powers of p? And that's not asking very much. Okay. Any questions about that? No. Okay. Right, and so just a little bit more notation. For an arbitrary field extension, we can define this kind of relative Galois cohomology to be the kernel of this restriction map that we defined. Okay. So that yeah, so that's often useful. Okay. All right. Well, let's actually do something. Finally, this is all pretty formal, right? Let's actually compute some Galois cohomology groups, right? So here's the first theorem. I take any Galois extension, not necessarily finite, but by definition, Galois extensions, like what is a Galois extension? A Galois extension is a field extension that is algebraic, normal, and separable, right? So it is certainly allowed to have infinite degree, but it has to be algebraic. Then for all of the higher Galois cohomology groups of L are equal to 0. Okay, so again, another way of saying this is that, no, I don't want to say it that way. Okay. If you restrict it to the case where it was the absolute Galois group, right, then this would be saying that, yeah, so in particular, this implies that HQK additive group is equal to 0 for all Q greater than or equal to. Okay, so the additive group is kind of acyclic for Galois cohomology is what we're getting out of this. Okay. This is sometimes called additive Hilbert 90 in contrast to the multiplicative Hilbert 90 that's coming up. Okay, but there's just a really good reason for this. The normal basis theorem is a theorem that applies to finite Galois extensions. What does it say? The normal basis theorem says that if you have a finite Galois extension, then what? You can find an element of the top field that if you take the orbit under the action of the automorphism group, then that gives you a K basis for the extension, right? So that I believe that would be a non-cohomological way of expressing the normal basis theorem. But if you think about that just for a little while, what does that really mean? It means that as a KG module, right? So again, if I have a field extension, if I have a Galois field extension, then the top field is certainly a K vector space, and it certainly has a K linear Galois action, right? And so any Galois extension is going to be a KG module. And what it's saying is that as a KG module, it's actually just isomorphic to KG. Okay. Right, so free of rank 1 as a KG module, that's an equivalent statement. You take whatever that magic element was that I was just telling you about in the statement of the normal basis theorem, that is your generator of L as a free rank 1 KG module. And so you think about that for a second and you say, well, what does that mean? Another way of saying that is that as a ZG module, that means that L is the tensor product of ZG from Z to, okay, whatever, of course, right? So, but that's the definition of induced, right? Induced means is obtained by tensoring from ZG to anything, okay? And so, which is the same as co-induced since G is finite. And again, induced equals co-induced modules over finite groups are cohomologically trivial. Okay, so here I put it's kind of hard to see, but there's a hat here. So in fact, and cohomologically trivial modules are in particular acyclic, even for Tate cohomology. So in this case, in the finite case, not only are the Q's equal to 0 for all Q greater than or equal to 1, but once you do Tate cohomology, so again, you reduce the H0 by modding out by the the image of the norm map. All of the Tate cohomology groups are equal to 0. Okay, so that does the finite case. How do you think we should do the infinite case?
take limits?
Yeah, so the best way to think about, often the best way to think about Galois cohomology or profinite cohomology of an infinite group is just obtained as a direct limit from the finite case. And often that makes things easy, and that's certainly the case here. So if G is infinite, well, like every profinite group, it is the inverse limit over its quotients by open normal subgroups. And so I do that. That should be a capital N. Okay, and so again, if you just think about the way these limits work, then yeah, so this was our main continuity theorem. So this cohomology is the direct limit over the suitable finite level cohomologies, and then L fixed by n is indeed going to be a finite Galois extension of K. That's just the way the Galois correspondence works. And so, and you look at all these and you say these are exactly the groups that I just said were 0 by step 1. So for all Q greater than or equal to 1. Okay, so basically the idea is that the additive groups are acyclic for Galois cohomology because at the finite level, the additive group is an induced module. Okay, so it's like the best. Somehow it's like the strongest possible way to show that the cohomology is trivial. Okay, so now comes the multiplicative Hilbert 90, aka Hilbert 90. Okay, so it's very similar to what has come before. First of all, instead of looking at the additive group, we have an arbitrary Galois extension. Okay. And then we take the Galois cohomology not with coefficients in the additive group. Now we take it with coefficients in the multiplicative group. But then the other difference is that I'm not claiming this for all Q greater than or equal to 1 anymore. I'm only claiming it for Q equals 1. Okay. And so as we'll see even later in this lecture, I believe, I'm certainly, boy, is this false if Q is greater than 1 in general. Okay, and so, yeah, so as usual, well, we see how the proof is going to break down. As before, we kind of immediately realize that now it suffices to reduce to the case of a finite Galois extension, and then the same kind of continuity argument will work. So how do you do this for a finite Galois extension? This is a classical argument. I'm going to do it very concretely. I'm going to take a 1 cocycle with values in the multiplicative group, and I'm going to show that it is actually a coboundary. So what does that mean? It means that I have to find an element of the multiplicative group so that for all sigma, or so maybe it'll turn out to be for all tau, doesn't matter, then the cocycle evaluated at tau is going to be like tau of some element divided by that element, okay, or the other way around. Okay, and so there's just a little field theory for this. By the independence of characters, so what does this mean? It means that if you have any, it's more general, but in particular, if you have any finite group of field automorphisms, then they're linearly independent. Okay, and so that's what I'm using. So the automorphisms, the L over K field automorphisms are linearly independent. And so now if what am I claiming? I'm asserting that there must be some element C in L such that this sum is not equal to 0. Well, why is that the case? Well, again, the characters are linearly independent, and so the only way that a linear combination could be 0, as a function from L into itself, is if all of the coefficients are 0. But okay, these coefficients are taking values in the multiplicative group, so none of these guys are equal to 0. Okay, and so therefore, just as a function, the sum over sigma in G of eta of sigma times sigma, so that's a function, by the linear independence of characters, that function must not be 0. What does that mean? It means I must be able to evaluate at something and not get 0. And okay, I think it's pretty clear. I wrote that C is an L. Well, gosh, if C were equal to 0, it sure looks like that whole expression would be 0. So I can say even more that magic element C had better be non-zero. Okay. And so using that magic element C, I'm going to build a magic element B, which is in fact the exact sum that I just said was not equal to 0. And I claim that basically that B is what I'm going to use to show that my cocycle is a coboundary. So, all right, so for all tau and G, well, I kind of crammed this in here. So if I take tau of beta, well, that's all I'm doing. I'm taking tau of beta. And then if I multiply that by eta of tau, well, I multiply that by eta of tau. And now I look at this and I say, oh, I get it. Eta of tau times tau of eta of sigma, well, it's a 1 cocycle. So that's going to be eta of tau times sigma. That's the only thing that's going on here. And then I'm going to have a sum over sigma of tau sigma, eta of tau sigma, and then I'm going to have a sum over sigma, and I'm going to have a tau sigma anywhere, everywhere. And so you know how that's going to go. So therefore, right. So therefore, the whole thing is going to be the sum over sigma of eta of tau sigma times tau sigma applied to C. And you know the standard argument: if I range over all elements of the group, including sigma, and then but now I'm ranging over all elements of tau sigma. So as sigma runs through all elements of G, so does tau times sigma. So therefore, the sum is the same if I just erase the taus. And if I erase the taus, that is my definition of B. Okay, and so what did I just show by doing this? I showed that eta of tau times tau of B is equal to B. Okay, everything is safely non-zero. So that means that eta of tau is actually equal to B divided by tau of B. Okay. And so what is that? But that's a coboundary. I mean, okay, maybe technically that's like the inverse of a coboundary. So a 1 cocycle is a coboundary if it is of the form, you know, sigma of x minus x. Here the group law is multiplication, but okay, the inverse of a coboundary is also a coboundary. Okay. So that's the proof of step 1. I mean, we literally just, you know, in a very concrete way, we contemplated a 1 cocycle and showed that it had to be a coboundary. Okay.
But is there any intuition for this? Like, what do we expect this B to work?
Why do we expect this B to work? I think maybe this is not a great answer, but I'm going to explain why this implies something that I'm going to call classical Hilbert 90, which is for finite cyclic Galois extensions. And then if you actually look at the proof of classical Hilbert 90, it might be somewhat similar. So yeah, that'd be my first guess. My first guess is that somehow we're reversing some argument for proving things about finite cyclic extensions. But yeah, anyway. I mean, there's other reasons. We think that Hilbert 90 should be true, of course, because of this principle of Galois cohomology that I was telling you about last time. So this L star is the automorphism group of a one-dimensional vector space, and so therefore, by the principle of Galois cohomology, this H1 should be parameterizing twisted forms of a one-dimensional vector space. But all one-dimensional vector spaces are isomorphic, so we kind of expect, you know, by general principles in Galois cohomology, we certainly expect this this group to be 0. But that's exactly wrong. If you're trying to prove a suitable version of this principle for Galois cohomology, if you follow any treatment like Serre's local fields or something, then in fact you want the non-commutative generalization of this, which I'm going to wave at later. If you had non-abelian cohomology, you can define the H1, and you can still show that H1G with coefficients in like GLN of L is equal to 0, and the same proof is basically going to work. And then using that proof, you can prove this this principle of Galois cohomology. But yes, that's not good. My best guess is that this is probably motivated by the classical Hilbert 90. Yeah, okay. All right. I don't know how directly. Let me actually just stop and quickly sneak a peek at in my field theory notes. I think I do this exactly the opposite way. I think I do prove classical Hilbert 90 classically. So let me see. Well, yeah, so I'm having a little bit of trouble. Sorry, it's kind of I found one part of it. Yeah, so maybe I shouldn't be looking at this right now. I can look at it later, but hold on just one second. Yeah, okay. I'm having, yeah, my notes kind of refer to something and then there's like a missing reference and so I'm having trouble, actually having trouble finding it at the moment. Oh, I just found it. Okay. Yeah. Yeah. Okay. So, yeah. So the proof of like the classical proof of Hilbert 90, or at least I found it in a special case. I'm finding it in the case where you have like a root of unity at least. So anyway, yeah. So I think in the proof of classical Hilbert 90, you use Dedekind's independence of characters, and so that gives some motivation. All right. Yeah. Wow, gotta fix up my field theory notes at some point. Anyway, so that completes the proof of the finite case of Hilbert 90, and then of course, you know, the argument for passing to the limit was general enough that it works verbatim in this case, and so we get the result for arbitrary Galois extensions. And in particular, yeah, so in particular, it says that if you apply this to the absolute Galois group of a field, then we get that sort of the additive group is totally acyclic for Galois cohomology, for all higher Galois cohomology. And it says that the multiplicative group is zero only, it's only telling us that the multiplicative, the H1 of the multiplicative group. Okay, and so, well, this is a little bit, so I think I wrote this down before I realized that like even later in this lecture, I was going to talk about the Bauer group. So we'll talk about the Bauer group, but the Bauer group by definition is second Galois cohomology with coefficients. Well, the cohomological definition of the Bauer group is that, and this does not have to be zero. Okay. Right, if and when we define non-abelian H1, then essentially the same proof would show that H1 with coefficients in GLN is also equal to zero, which again is very useful. And again, the motivation of this is that this is the automorphism group of a finite dimensional vector space. And so what are we saying? We're saying that if you have two K vector spaces that become isomorphic after extending them to L vector spaces, then they were already isomorphic as K vector spaces, which is completely obvious because the only isomorphism invariant of a vector space is its dimension, you know, and of course, whatever the K dimension of a vector space is the L dimension of the vector space tensored from K to L. So that's in some sense, this result is clear from an interpretation in terms of twisted forms, although again, logically it goes the other way. All right, so let me do the classical Hilbert 90 at this point. So suppose we have a finite cyclic Galois extension, and so what does that mean? It's Galois, and the Galois group is a cyclic group of order n. Let's let sigma be a generator, and then the classical one says that for an element upstairs, the trace is 0 if and only if you can write the element as alpha minus sigma alpha, where sigma is any generator of the Galois group. And then the norm is equal to 1, exact multiplicative analog, if and only if you can write it as something divided by sigma of that same thing. Okay, and I guess I gave some argument here for it's completely obvious, even if the extension is not cyclic, that you can go from right to left. It's pretty clear that using the multiplicative, the norm map is multiplicative, and the norm of alpha is the same as the norm of all of its Galois conjugates. So sure, the norm of this thing is equal to 1. The trace is additive, and the trace is equal to all of it. The trace of an element is equal to the trace of its Galois conjugate. So certainly the trace of that is 0. By the way, once I turn the page, we're going to get both directions at once. So yeah. It's actually kind of better to look at the, well, okay. The point being that we actually know how to compute cohomology of cyclic groups, so good for us, right? So the first cohomology is the minus first, because we have this twofold periodicity in cohomology of finite cyclic groups, as we discovered, using a specific resolution. We get that it's the minus first Tate cohomology, which is the 0th Tate homology. So whereas the normal H0 is what you call it, the covariance, and so you mod out by the image of, you mod out by M modulo IM, which is the image of the augmentation ideal because it's cyclic. The augmentation ideal is just generated by sigma minus 1. But it's not normal H0, it's Tate H0, so it shouldn't be the entire module, it should only be the kernel of the norm map. And this is kind of funny because the norm map is kind of an abstract thing. If the thing is acting on, you know, a finite group is acting on a module, then the norm map is the, you know, is the sum of all the elements in the group. But now because in this particular case, the norm is precisely the trace, right? So this came up before. The norm acting on the additive group of L is, you know, you take an element of L and you send it to the sum of, take an element X in L and you send it to the sum of sigma X as sigma ranges over all elements of the Galois group. And that's a wonderful thing in field theory. It just so happens it's called the trace rather than the norm. And so, well, gosh, we proved it because, oh, right, what did we just, we know that this is equal to 0. That's what we just proved, right? And so to say that this is equal to 0 means that you have trace 0 if and only if you're equal to, if and only if you're of the form sigma of something minus something. Okay, so the result comes right out of that. And then the case of the multiplicative group works exactly the same way. By Hilbert 90, that's equal to 0, and it's exactly the same discussion. And in this particular case, the abstract norm map turns out to be what we call the norm map in field theory. And everything is multiplicative rather than additive. And so therefore, the kernel of this thing are the ones where the norm is equal to 1. And so you see that since this quotient is equal to 0, indeed, your norm is equal to 1 if and only if you're of the form sigma minus 1 of something. So great, that was the classical Hilbert 90. And again, I think, you know, I think Hilbert proved this last thing. And again, though, yeah, I'll have to go back and fix it. But I, I think that if you maybe by squinting at it for a little bit, I think you'd go the other way. I think you could look at the classical proof of Hilbert-Hindy and try to figure out how to do the proof that we did in the general case. Okay. So let's do, so there's some nice corollaries here. So now we get a form of Kummer theory for the multiplicative group. Kummer theory for the multiplicative group is often called Kummer theory. You could pursue Kummer theory for any commutative group scheme, but the classical case is the multiplicative group. So you take suppose you take a positive integer that is not divisible by the characteristic of your field. So no restriction in characteristic 0, in characteristic P, n should be prime to B. So by mu n, I mean in fact the n torsion subgroup of the multiplicative group of K sub, so that those are the nth roots of unity in an algebraic closure, and because of this characteristic assumption, that there are going to be n nth roots of unity, and they're all going to live in a separable closure. And so the claim here is that Galois cohomology. So yeah, so this mu n, maybe I'm going a little quickly. This mu n a priori, is a submodule of is a subgroup of the multiplicative group of K sep. But of course, if you have an nth root of unity and you hit it with a field automorphism, you get another nth root of unity. So the set of nth roots of unity is a GK submodule. Okay, and so the claim is that the first Galois cohomology with coefficients in the nth roots of unity is the group of nth power classes. Okay, K star mod K star to the n. Well, why is this true? It's immediate. Well, I just told you mu n is defined as the kernel of this short exact sequence of discrete Galois modules. So you take Galois cohomology, right? And you're going to get, what are you going to get? You're going to get 1 into mu n of k, into k star, into h1 mu n. And then the next two terms are going to be 0 precisely by Hilbert's theorem 90. And you just listen to what I said, and you get that the co-kernel of multiplication by n is going to be isomorphic to h1 with coefficients in mu. Okay. So that's nice. That's the cohomological version, which is a little bit more general. There's something nice to say if you would now assume that K contains a primitive nth root of unity. So we may, in general, this might not hold for K. So maybe you have to pass to K adjoin the nth roots of unity. Well, what's the point of that? Well, that makes, if you already have all the primitive nth roots of unity inside K, well, K is the Galois invariance of K sep, and so that's equivalent. The assumption that K contains a primitive nth root of unity is equivalent to the assumption that mu n is has trivial Galois action. Okay, and then again, by convention, if we want Z mod nz means the finite group Z mod nz with trivial Galois action. Okay, so we don't write, whenever we write down Z mod nz as a Galois module, we always mean with trivial action. And so therefore it's that, and then we know that H1 with coefficients in a trivial module is literally just the Hom. The twisted part of the cocycle goes away, and the co-boundaries are just 0, so it becomes Hom. And so this recovers classical Kummer theory. There's several ways of saying this, and different consequences that you can get from it. So let me just mention one of them. This is telling us something about. It's saying that the group of nth power classes is Pontryagin dual to a certain quotient of the absolute Galois group of K. So let me try to set that up a little bit. Reminder. If you've seen it before, definition, if you haven't, there's a beautiful duality on the class of locally compact abelian topological groups. People say LCA group, they don't say LCC group, so I'm going to say abelian here. Yeah, so this is a generalization of Fourier series and Fourier transforms, by the way. So it really is what's a duality? It's like so it's like an anti-equivalence of categories that if you do it twice is the identity. Okay, so it's a duality kind of in the most classical sense. If you can any locally compact abelian group will have a Pontryagin dual group, which is also a locally compact abelian group. In general, the dual will not be, isomorphic as a topological group to the group that you started with, but it will be canonically isomorphic to its second dual. That's kind of what duality, the most familiar thing that duality would mean. And so how do you define the Pontryagin dual group? It's continuous homomorphisms from G into the S1, the unit circle, as a subgroup of, the multiplicative group of the complex numbers. But so that tells you what it is. I mean, it's visibly a commutative group. What's the topology? It's the natural function space topology called the compact open topology. I won't review that right now. For our purposes, a special case of this is more pertinent. So this duality restricts to a duality between profinite abelian groups. So equivalently, if your locally compact group is moreover compact and totally disconnected, then as we know, that makes it an inverse limit of finite discrete groups. And then what should a duality do to an inverse limit of finite discrete groups? Well, Pontryagin duality is also generalizing the much more elementary duality between a finite commutative group and itself, right? So every finite commutative group is non-canonically isomorphic to its character group, the group of homomorphisms into C star, which automatically land inside the unit circle, right? So there's this natural duality between finite commutative group and itself, which are isomorphic. And so if you know that duality and you have a sense as to how duality should mess with limits, then I guess I'm not writing it down, but here, this inverse limit of, if I take an inverse limit of finite groups, and then I take a Pontryagin dual, you would expect or hope that to be the direct limit of the Pontryagin dual groups. And so that's how it works. And that gives you a duality between profinite abelian groups and discrete abelian torsion groups, okay? These are the inverse limits of finite discrete groups. These are the direct limits of finite discrete groups, okay? And if you're doing that kind of Pontryagin duality, you can just check that S1 is more than you need, in the sense that if your group is either profinite or discrete torsion, then any homomorphism into S1 will land inside the torsion subgroup of S1, which is Q mod Z. Q mod Z being thought of as the roots, all the roots of unity in S1. Okay, so that's Pontryagin duality. And so what's the relevance here? Yeah, so Kummer, this interpretation of Kummer theory is as follows. So I take any field containing a primitive entry of unity. So I have the GK is the Galois group of K. So I can do two things. I can abelianize it as a topological group. So I can mod out by the closure of the commutator subgroup. That will give me the abelianization, which is canonically, so that's a quotient of the original Galois group. Every quotient of the absolute Galois group via a closed subgroup by the Galois correspondence is still going to be the Galois group of some intermediate Galois extension. So if I abelianized it, that would give me the Galois group of the maximal abelian extension. But now I want to do more. Now I only want to look at the Galois group of the maximal abelian extension that has exponent dividing n. Okay, so this is going to be an inverse limit of all finite Galois extensions where the automorphism group is a commutative n torsion group. Okay, and so again, you can think of that Galois theoretically, or it would make sense to take any profinite group and consider the quotient of it, which is abelian and of exponent dividing n. Excuse me. Okay, right. And so the Kummer theory is telling us that the Pontryagin dual of this group, this is a profinite group, its dual should be a discrete group, is the group of nth power classes. Okay, so that's a nice way of thinking about classical Kummer theory. Okay. Again, you could say more. You could go in and say, I have a particular, how do I get a particular cyclic n extension, and that's going to have a cohomological interpretation as well. Okay. So now I want to move on to Artin-Schreier theory. So Artin-Schreier theory is kind of the characteristic P analog of Kummer theory. So you see that Kummer theory has a problem in positive characteristic because n has to be prime to P. And so, well, you know, in general, mu n would split as the product of its CELO P subgroups. And so, you know, if you could give me some analog of Kummer theory for cyclic extensions of prime power order, I'd be much happier. Okay. And no, I'm not going to do all of that, although it has been done. I'm going to give you the analog for cyclic P extension. So that's called Artin-Schreier theory, which came up in the last course as well. So if you have a field, okay, see ya. If you have a field of characteristic P positive, then this funny map x to the P minus x, which doesn't look like a group homomorphism, is definitely a group homomorphism in characteristic P, thanks to the magic of characteristic P. It's actually an isogeny of the additive group. If you want to say it that way, what does that mean? It means that it's a, you know, it's an algebraic homomorphism, algebraic endomorphism of the group scheme. It's surjective in the geometric sense and has finite kernel. And all of those things are easy to see. So the kernel is the elements in a field for which x to the P is equal to x. Oh, I know that's FP. So the kernel is FP, just a finite kernel. And yeah, it's surjective because over the separable closure, because what does surjective mean? It means that for any alpha in the separable closure, I want alpha to be of the form x to the P minus x for some x in the separable closure. But yeah. The whole point of this is that x to the P minus x minus alpha is most certainly a separable polynomial. Its derivative with respect to x is -1. That's awesome. So it's separable. And so therefore, all the roots of this do indeed live in the separable closure. So yes, this map is a surjective group homomorphism, and its kernel is FP. And certainly, certainly FP is stable under the action of Galois. Okay, so if we take the Galois cohomology here and use the additive Hilbert 90, okay, so this is funny. It's like a somewhere between an additive and a multiplicative version of Hilbert 90. If we do that, we take the, you know, just, I mean, nothing to see here really. I mean, you do the cohomology and you say, okay, so I'm going to get FP into K under rho into Hom H1. This is trivial, so Hom of Galois group into FP into 0 by additive Hilbert 90. And so you compile that the same way, and you see that K modulo the image of K under this Artin-Schreier isogeny is isomorphic to Hom from GK into FP. Okay, so that's very useful. So this is a form of Artin-Schreier theory. And so again, if you want to express this in terms of what is this telling us about the Galois group of GK or a certain piece of it, this is saying that the Galois group of the maximal abelian extension of exponent P is Pontryagin dual to this slightly weird looking thing, right? So this group is being in analogy to the group of nth power classes on the multiplicative group. And then if you've never seen this before, at some point you can do exercises to try to figure out like what this quotient actually, I mean, the definition is, so it's, elements of K modulo elements of the form x to the P minus x. I mean, that's what it is. But, you need some practice, I think, in thinking about, is that a big group or whatever? And so, yeah, so if you remember, a couple lectures ago, I mentioned that the absolute Galois group of a Laurent series field over a finite field, so FQ double round brackets T, was not small because it had infinitely many separable extensions of degree P. This is how you would prove that. I claim that if K is a Laurent series field over a finite field, so a local field of positive characteristic, it is just, I mean, it's not immediate, but it's just some elementary exercise involving power series. you can prove that this Arden-Schreier quotient is infinite in that case, and that tells you that that the maximal commutative, it tells you that the maximal extension that is Galois abelian and of exponent p is infinite. And if you think about that, then that tells you that every extension of fields that is Galois and abelian of exponent p is a composite of cyclic p extensions. And so if the whole thing is infinite, then there must be infinitely many cyclic p extensions. Okay, so this is how you would prove that the absolute Galois group of a local field of positive characteristic is not a small profinite group, even though the absolute Galois group of a p-adic field is a small profinite group. Yeah, so then I'm just waving at it here, but again, this is not completely satisfactory. You kind of ask yourself, well, okay, you told me, you gave me a beautiful description. You're being generous, I guess. You gave me a beautiful description of the Pontryagin dual of the maximal abelian extension of exponent dividing n when n was prime to the characteristic. I love that, nth power classes. You gave me a kind of weird but satisfactory description of the, in characteristic P, you gave me a description of the P part. Again, you should tell me what the P to the N, the P Galois group is, and then I can understand. And then I feel like I'll understand the entire, abelianized Galois group, at least, here. But this one is actually better than this one, by the way, because here you have to have the nth roots of unity. And here there's no condition. Anyway, so it's natural to want to supplement Arden-Schreier theory with cyclic p to the n extensions instead of cyclic extensions. And there is such a thing. It was done by Witt. And so you put something a little bit more, it's the same Arden-Schreier isogeny, kind of, but it's not the additive group anymore. It's some Witt vector group, which I guess I just don't have time to talk about. As a scheme, this Wn is isomorphic to additive group to the n, but the group law is twisted and more interesting. Anyway, so there's this Arden-Schreier Witt business. Okay, and so yeah, again, more details on any of this would make for a nice Friday lecture, I think. Okay. I was going to talk about Brouwer groups. It's kind of the beginning. I think this is a reasonable place to stop, actually. I was going to say more about Brouwer groups than was on this one page. I guess I'll just say this. Again, for a Galois extension L over K, I'm going to define the relative Brouwer group BL over K to be the kind of relative Galois cohomology. So second Galois cohomology of the Galois group with coefficients in L, and then so then the Brouwer group of K is the Brouwer group of K sep over K, which is second Galois cohomology with coefficients in the multiplicative group. Okay, and so this, yeah, let me get out without saying everything that I just said. So whereas Hilbert 90 says that the first Galois cohomology is always 0, boy, does this thing not have to be 0. We'll do some examples. It's a very interesting invariant of a field, the Brouwer group. If you pick a field at random, it is certain to be a really big torsion group. There are some nice examples that we can do. But this is not just a nice example. Knowing the Brouwer group of a local field is going to be a big piece of the local class field theory that we're trying to do. So one of the things that we'll do, probably rather sooner than later, is to compute the Brouwer group of a local field. It's not 0. Okay. Any questions? All right, well, we went for like an hour. That seems sufficient. Yeah, so I owe you I need to upload like the last 3 lectures, I think, including this one. So I will get to work on doing that. So see you on Friday.